In this lecture, we're going to be taking a look at the ideal inverter. So an inverter is a device that takes electrical energy in the form of direct current and converts it into alternating current or AC form at the output. So there are many applications for inverters. Basically, anytime that you have a DC source, but you have devices that take power in the form of alternating current, then you need to have some means of converting the DC source into alternating current such that you can use that power. So for example, let's say that you have a backup battery at your house for when the power goes out. So usually there's power in, you charge the battery, but then the power goes out and you need to use the energy that's stored in the batteries to power devices in your house. However, batteries work in DC form, so the energy is stored in DC form. So you need to have a means of converting that DC source into alternating current or AC form such that you can power up devices like blenders or light bulbs or TVs or basically any household appliance. Now another common application of inverters is for solar applications. So solar panels generate power in the form of direct current. But again, most devices use power in the form of alternating current. So you will need to have a means of converting the DC power that's generated from the solar cells into alternating current such that you can use it. So let's go ahead and draw the symbol for this device. So you would have an input voltage, Vin, that's going to be of the DC form. And you're going to feed that into some device. And we're going to draw a black box for now. And then you have an output voltage, V out. And this is going to be of alternating current form or AC form. And let's also define the input current, I in, and the output current, I out. And so usually what you're going to see for an inverter is that at the input you're going to see the DC symbol. So remember that the DC symbol looks like this, and then the alternating current symbol looks like this. So it's basically a flat voltage at the input and a sine wave at the output. So now let's go ahead and draw the input voltage and the output voltage in a pair of axes to see how this device works. So we're going to say that the input voltage is a perfect DC voltage. So Vn is right here. And let's say that this magnitude is V. Now what we would want ideally is for the output voltage to be a perfect sine wave. So it will look like this. And ideally the peak magnitude of the sine wave is going to be equal to the magnitude of the DC voltage. So this point right here is going to be V. And then the negative peak, so this point right here, is going to be minus V. So notice here that I've drawn the output voltage as a perfect sine wave. So it has no distortion on it. It's perfectly a sinusoidal signal. And this is ideally what we would want. Basically, in more technical terms, we have a sine wave that has only one frequency component. And so typically the frequency of this would be either 60 Hertz in America or 50 Hertz in Europe and other parts of the world. But this sine wave output would have only that frequency component. It wouldn't have any other frequency components. So it's a perfect sine wave. Now, more practical applications, that's not really what's going to happen because we have some switching that we have to do inside the inverter to achieve this sort of sinusoidal output. So more practically, the output voltage would look more like this. So it's going to be sort of a sine wave, but with several steps in it. And we're going to see why that's the case in the next couple of lectures. So, but again, that's a practical application. Ideally, if we could make a perfect circuit, we would want the output voltage to be a perfect sine wave. Now, something else to note here is that the input power in DC form, so we're going to say that P in DC for an ideal inverter is going to be equal to the output power in AC form. So basically we're saying that there's no loss inside the inverter itself. All the power that's being fed in DC form is being outputted in alternating current form. Now this device that I've drawn here is what's called a single phase inverter. But inverters can also be of the three-phase configuration. So just like the single phase, we're going to have for a three-phase inverter an input voltage Vn. And that's going to be the same as in the single phase because that's a DC voltage. And then we're going to have a black box. But now we're going to have three output voltages. So we're going to say that this would be VA, VB, and VC. Now again, this would have the DC symbol here at the input and the alternating current or AC symbol at the output. So we draw these waveforms in a pair of axes, they would look like this. Where this is VA, VB, and VC. So basically we have a balanced three-phase set of sine waves at the output for the three-phase voltages. And again, this would be for an ideal inverter, meaning that just like in the single-phase example, there's no distortion in the output voltage. And also again, just like in the single-phase example, in practical applications, because we're using power semiconductor switches inside the inverter, they're going to look more like waveforms with several steps in it, kind of resembling sine waves, but not perfectly a sine wave. Okay, so now that we've looked at what an ideal inverter looks like, let's take a look at actual inverter circuits.